Right now, as you watch this, you are inside a bubble, not metaphorically, physically. There is a boundary around you, around all of us, beyond which nothing we will ever build, no space mission we will ever launch, no signal we will ever send, can reach. Not because of distance, because of time, because the universe is expanding faster than light can cross it. Everything you have ever seen in the night sky, every star, every planet, every galaxy photographed by Hubble or the James Webb sits inside that bubble. We call it the observable universe, 93 billion light years across, roughly 2 trillion galaxies. It sounds enormous, and it is enormous, but it might be the smallest thing in existence. Because beyond that boundary, beyond what we can ever see or measure, the universe keeps going. We just have no idea what it looks like, or whether the rules that govern everything you know still apply there. That is what this video is about, not what we know, what we can't know, and why that distinction might be the most unsettling thing in all of science. Before we go beyond, we need to understand exactly what we mean by the boundary itself, because most people misunderstand it. The observable universe is not the edge of the universe. There is no wall out there, no sign that says the universe ends here. The boundary is not a physical place. It is a limit of information. Here is how it works. The Big Bang happened approximately 13.8 billion years ago. Since then, light has been traveling towards us from every direction. The furthest light that has had time to reach us, light that set off almost at the moment of the Big Bang, defines the edge of our observable universe. Beyond that distance, light simply hasn't had enough time to arrive. Not yet. Maybe not ever. But here is where it gets strange. Because space itself has been expanding the entire time that light was traveling, the objects that emitted the oldest light we can see are now much further away than 13.8 billion light years. In fact, the edge of the observable universe sits roughly 46 billion light years away in every direction. The observable universe has a diameter of about 93 billion light years. That is not a typo. The universe is older than 13.8 billion years in terms of travel time, but larger than 27.6 billion light years in terms of physical distance. Space expanded while the light was in transit. Now here is the first perspective I want you to sit with. Inside this 93 billion light year bubble, there are an estimated 2 trillion galaxies. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. The observable universe contains more stars than there are grains of sand on every beach on Earth, by a factor of roughly 10,000. And that is just the part we can see. The CMB, the cosmic microwave background, is the oldest light we can detect. It is the afterglow of the Big Bang, now stretched into microwave frequencies by the expansion of space. It reaches us from a distance of about 46 billion light years, from a time when the universe was only 380,000 years old. Beyond the CMB, we are blind, not because there is nothing there, but because before 380,000 years after the Big Bang, the universe was so hot and dense that it was opaque. Light couldn't travel freely. We cannot see before that point. We cannot see beyond the CMB. So everything we know about the universe, every galaxy ever photographed, every planet ever detected, every black hole ever measured, exists inside a sphere defined by the time light has had to reach us. What sits outside that sphere is the real question. The most straightforward answer to what exists beyond the observable universe is more of the same. More galaxies, more stars, more planets, more black holes and nebulae and voids and filaments. The same universe, just the part we cannot see. This is actually the leading scientific view. And it is simultaneously the most boring and the most terrifying possibility. Here is why. Modern measurements of the cosmic microwave background, particularly from the Planck satellite, tell us that the universe is, to an extraordinary degree of precision, spatially flat. Not curved like a sphere, not curved like a saddle, flat. This matters enormously, because the geometry of space determines whether the universe is finite or infinite. If the universe has positive curvature, like the surface of a sphere, then it would eventually loop back on itself. Travel far enough in one direction, and you'd return to where you started. The universe would be finite, with no edges, but with a finite volume. If the universe is flat, the simplest mathematical solution is that it extends infinitely in all directions. Infinite space, no edge, no center, no boundary, just more and more, forever. If that is true, and the data suggests it might be, then beyond the observable universe, there is an infinite expanse of space filled with matter and energy obeying the same physical laws we know. But this is where I need you to really think. If the universe is infinite, then every possible arrangement of matter that can exist does exist. Somewhere. Infinitely many times. Think about what that means. There are a finite number of ways that the particles in a region of space can be arranged. Quantum mechanics gives us that, which means that in an infinite universe, every possible configuration of matter repeats. Forever. There is a region of space, not in another dimension, not in a parallel universe, but in our own universe, just beyond what we can see, where a planet exists that is arranged, atom for atom, identically to Earth, where you exist, having this exact conversation, where you make every possible different decision you could have made, not as philosophy, as mathematics. If the universe is infinite and matter arranges itself randomly, this is not a metaphor. It is a statistical certainty. This is called the level 1 multiverse in cosmological theory. It requires no new physics, no exotic dimensions, just infinite space and the mathematics of probability. The distance to your nearest identical copy, roughly 10 to the power of 10 to the power of 28 meters. A number so large it has no name. A number so large that writing it out would require more digits than there are atoms in the observable universe. But finite. In an infinite universe, that distance is just a number. Now let's go further, because more of the same is only the first possibility. The second possibility is more unsettling. What if beyond the observable universe, the laws of physics are different? This is not science fiction. This emerges directly from one of the most successful physical theories we have, cosmic inflation. Inflation is the theory that in the first fraction of a second after the Big Bang, we're talking 10 to the minus 36 seconds, the universe underwent a period of exponential expansion. Not fast expansion. Exponential. The universe went from smaller than a proton to roughly the size of a grapefruit in an almost incomprehensibly short time. Inflation explains several things about our universe that would otherwise be deeply puzzling. Why is the universe so uniform in temperature across regions that should never have been in contact with each other? Inflation. Why is the universe so precisely flat? Inflation. But inflation has a consequence that its architects didn't initially intend, and that many physicists find both beautiful and deeply disturbing. In most inflationary models, inflation doesn't stop everywhere at once. It stops in some regions, like ours, while continuing in others. The regions where inflation stops form what we might call bubble universes, islands of normal expansion in a still inflating sea of space. This is called eternal inflation, and it implies that beyond our observable universe, and beyond the larger region that formed from the same inflationary event, there are other bubbles, other universes, potentially infinite in number. Here is the critical part. When inflation stops in a region and a bubble universe forms, the physical constants of that universe, the strength of gravity, the mass of the electron, the value of the cosmological constant, are determined by the energy state of the inflating field at that moment. Different bubbles, different energy states, different physical constants. In some bubbles, gravity might be slightly stronger. Stars would collapse before planets could form. Life, as we know it, would be impossible. In other bubbles, the cosmological constant, the energy of empty space, might be larger. The universe would expand so fast that matter could never clump together. No galaxies, no stars, no chemistry. Our universe appears to be extraordinarily finely tuned for the existence of complex structures. Physicists have calculated that if the cosmological constant were even slightly larger than it is, by a factor of roughly 10 to the power of 120 in some estimates, the universe would be sterile. No stars, no planets, nothing. The inflationary multiverse offers one explanation for this fine-tuning that doesn't require a designer. If there are infinitely many bubble universes with varying constants, then by definition we find ourselves in one where the constant permits our existence. We couldn't be anywhere else. This is called the anthropic principle. It's either a profound insight or a deeply unsatisfying non-answer, depending on which physicist you ask. The debate is ongoing and genuinely unresolved. But here's what I want you to take from this section. Beyond the observable universe, there may exist regions of space, possibly infinitely many of them, where the rules that govern everything you know simply do not apply, where atoms cannot exist, where time might behave differently, where the concept of a stable physical reality has no meaning, not another dimension, not a movie multiverse, just space, governed by different mathematics. Now, I want to be precise with you, because this is where popular science often loses its honesty. Everything I have described so far, the infinite flat universe, the eternal inflation multiverse, these are legitimate scientific theories. They emerge from real mathematics, real physical models, real observational data. But they share something important. They are untestable, at least with any technology we can currently imagine. The observable universe is bounded by the cosmic horizon. Nothing from beyond that horizon can reach us. No light, no signal, no information of any kind. Whatever exists beyond that boundary is, by definition, causally disconnected from us. It cannot influence us. We cannot influence it. We can never verify it directly. This creates a genuine philosophical problem for physics. A theory that makes no testable predictions is, by the standards of science, not science. It is metaphysics. Many physicists, including serious credentialed ones, argue that the multiverse in all its forms falls into this category. Others argue that a theory can be scientifically legitimate even if we cannot test it directly, as long as it emerges necessarily from theories that are testable. Inflation is testable. Its predictions about the CMB have been confirmed. If eternal inflation follows necessarily from inflation, perhaps it inherits some of that legitimacy. This debate is not settled. It is one of the most interesting arguments in contemporary physics, and it sits precisely at the boundary between science and philosophy. But here is what no one disputes. The observable universe, the 93 billion light-year bubble we inhabit, is almost certainly not the whole universe. The data from the CMB, from galaxy surveys, from our best cosmological models, all point to a universe vastly larger than what we can see. Whether that larger universe is 10 times bigger, a trillion times bigger, or genuinely infinite, we cannot say. The James Webb Space Telescope, which has been transforming our understanding of the early universe since 2022, is already finding galaxies that challenge our models of how quickly structure can form. In 2025 and into 2026, JWST has been returning data on galaxies from when the universe was only a few 100 million years old, and some of them are bigger, brighter, and more structured than our models predicted they should be. The universe keeps surprising us at the edges of what we can see. That pattern is unlikely to stop at our horizon. There is also something worth sitting with. The cosmic horizon is not fixed. As the universe ages, more light has time to reach us. The observable universe grows by roughly 1 light-year every year. We are slowly, very slowly, seeing more. But against this, the accelerating expansion of the universe works in the opposite direction. The most distant galaxies we can currently see are receding from us faster than light, not because they are moving through space, but because the space between us and them is expanding. Eventually, galaxies that are currently visible will cross our horizon and disappear from view forever. The observable universe will shrink, not grow, in terms of what we can observe. Future civilizations, if they exist, will see a lonelier universe than we do. The evidence for the Big Bang and the wider cosmos may eventually become inaccessible, locked outside an ever-contracting horizon. That is one of the stranger implications of dark energy. The universe is not just expanding. It is accelerating away from us, taking our evidence with it. There is one more angle I want to cover, because it changes everything about how you should think about the boundary. We've been assuming that the universe is simply space, that it extends in the directions we are familiar with. But the shape of space itself is an open question. Flat space, as I mentioned, implies infinite extent, but flat is a statement about curvature, not topology. A flat space could still wrap around on itself in strange ways. The mathematical equivalent of a video game where walking off one edge brings you back on the other side. Some physicists have proposed that the universe might have a topology like this, that if you traveled far enough in one direction, you would eventually return to your starting point. There have been attempts to look for this in the CMB. A wrapped universe would produce specific repeating patterns in the microwave background. So far, no such patterns have been conclusively detected. The universe appears, to the limits of our measurement, to be simply and straightforwardly flat. But, to the limits of our measurement is doing a lot of work in that sentence. The observable universe is roughly 93 billion light-years across. If the universe wraps around on a scale larger than that, we could never detect it. The repeating patterns would be beyond our horizon. The honest answer to the question of the universe's shape is we don't know. We know it is very close to flat. We know it is very large. Beyond that, our certainty runs out. So, what really exists beyond the observable universe? The honest, scientifically grounded answer is this: almost certainly more universe, more space, more matter, more structure, more galaxies arranged in the same cosmic web we observe here. Possibly infinite amounts of it. Possibly regions where the same laws apply, but different arrangements of matter have played out every possible version of history, including versions that include you. Possibly regions separated by the remnants of eternal inflation, where the physical constants differ, where atoms don't form, where what we call reality has no equivalent. And beyond all of that, beyond the mathematics and the models and the extrapolations, a boundary that we will never cross, a horizon that is not a wall, but a limit of information, beyond which the universe exists, doing whatever it does, entirely without our knowledge. Here's the question I want to leave you with. Does it matter? Does it change anything about your life, your decisions, your sense of who you are, that beyond the reach of every telescope we will ever build, the universe continues in ways we cannot know? Most people would say no. The unobservable universe is irrelevant to everything we do. In my honest opinion, I think this is not true. I think the existence of a boundary, a hard limit on what can ever be known, is one of the most important facts about our situation. It means that the universe contains truths that no intelligence, no matter how advanced, will ever access. That reality is larger than knowledge. That there are questions with answers we will never find. That is either the most humbling thought imaginable or the most freeing one. I'll leave you to decide which.